Yep, thanks for the introduction, and that's a very nice summary of what I'm going to talk about. So I'm going to be talking about average case voting, and this is mostly based on joint work with Shadin and David when I was a PhD student at USC. All right, and also, I don't have a lot of content, so feel free to interrupt. And I chose not to present too much technical details, so just feel free to ask any questions. Good. Right, so if you're here today, you're probably very familiar with this. So we're going to study the problem of voting. So you have some candidates, and then you solicit preferences, permutations from each voters, and then some voting rule is going to decide a winner. So throughout this talk, we're going to focus on elections where there's a single winner. And we're going to take the utilitarian approach where everybody has a numerical score for each candidate. Or in this talk, we're going to handle costs. So, so there's a cost, which is simply when you put the voters and candidates in the metric space, it's just a distance from your voters to candidate. Okay, so, and then you can measure the cost of a candidate again. So, this is all the same for talks today, just as the average distance to the voters, or the sum of the distance is the same thing. Now, when you fix an election rule, suppose you want to do plurality on this particular instance, the voters are going to vote like this, and this green figure is going to win with 5 votes. And but perhaps it turns out this red figure is the is a candidate with the lowest social cost. So you can define a distortion of your rule on this instance. Okay. All right, good. So what's the upshot of having this model? When you put everyone in a metric space and you ask for distortion, it allows us to study the worst case distortion of voting rules, which is just defined as the maximum possible distortion you can have over all instances. And you can study upper and lower bounds for this, as you've seen in the previous 2 talks. Right? And also, perhaps more importantly, it allows you to compare voting rules quantitatively. Right? So in the past, historically, we've often studied this through an axiomatic approach, which just like errors and possibility theorem and so on. But this now allows you to say how much better is a voting rule compared to other rules if worst case distortion is what you believe in. And this is exactly what motivates our work. So we just want to raise questions on this worst case distortion. So this is the punchline, the motivating question is, what about average case distortion? I say this motivation is pretty natural for me because it's a similar situation that in the study of, say, algorithm and complexity, like worst case analysis does give you very good results, beautiful results sometimes, but it very often does not apply to problems that you run into in practice. And that's why very often it would be useful to have some average case analysis, average case understanding to your problem. Okay. All right. So without further ado, let me introduce just one slide, the main contribution of this line of work. So what we did was we just consider representative candidates where we go with the most natural notion that we think is just your candidates are drawn independently at random from your voter population. Okay, so instead of maximizing over your instance to find the worst case distortion, you just compute the maximum possible expected distortion instead. So the only thing you choose is your voter distribution and your voting rule. After that, this quantity can just be computed where the candidates are drawn IID. All right. Any questions? So this is the most important thing. So instead of studying the worst case, you study this quantity, which is one notion for average case voting, and is the notion that we went with.
So just a quick question. So
Yeah.
about the alternative, doing the expected cost divided by the, pushing the, rather than expectation of the ratios, doing ratio of expectations, that would be harder, or have you considered that?
Right. We have some results on that in one of the papers, I feel. Yeah, I feel it's not really, sometimes it's very similar mathematically, but also it could be quite different because just how the, these operations, they do not really commute, right? They're not the same thing. So yeah, we just felt this notion was more natural, and we went with this one.
Okay, thanks.
Yeah, but that's a perfect valid notion too. It's one of the open problems that you can ask, what are the other notions of average case voting or average case bipartite matching, or any your favorite problem. And I think these are all very good questions. All right, anything else? Any other questions? Okay, good. All right, so once you decide to go with this model where your candidates are drawn ID from the voter population, you can ask questions like the following. For example, you can ask, now that the candidates are representative, are the voting systems more effective? And also you can ask, by how much, what is a gap? Are they compared to the worst case analysis now? If I examine all these voting rules in the average case, what do they look like? Does this offer some other spectrum of how the voting rules lie in terms of effectiveness? Okay. All right, so the results I'm going to present in this talk can be roughly partitioned into two parts. The first part will focus on just the election with two candidates, and then the second part will focus on election with multiple candidates. Let me give you a quick summary, a quick highlight of the results in these two parts. Okay. So for two candidates, we focus on election with majority rule. As mentioned in some of the previous talks, this is probably the only rule that makes sense for two candidates because you only observe the preferences, not the actual metric space. Okay. So we show that informally, that when you have representative candidates, it does decrease the distortion you can incur. Okay. And also the amount of how this gap depends on the complexity of the underlying metric space. So if you have a line, then the distortion becomes much smaller, but if you have a general metric space, it doesn't go down that much. Okay, all right. So that's the result for two candidates. So for multiple candidates, we give, so we focus on a family of voting rules. It's called positional voting rules. They contain a lot of the well-known voting rules like plurality and veto and border. So we give a clean and tight characterization of which rules have constant distortion, which means it doesn't scale with the number of candidates and voters. And perhaps more surprisingly, we note that moving to the representative candidates model actually allows us to distinguish different voting rules that look the same in the worst case metric voting literature. All right. Okay, so now I'm going to move, before I move on to the details of these results, any questions? All right, good. Okay, so now we're going to move on to the first part, which is a majority rule election between two candidates. So perhaps it would be helpful to start with this example of distortion 3. I will go over this quite quickly. It's probably not the first time you've seen this example in this workshop. So you just have two candidates, the blue and green figure, and the red arrow specifies the voter distribution. Okay? You can compute the cost of these two candidates. They're roughly a factor of 3 away from each other. Unfortunately, in this case, the green figure is going to win because he's going to gain all the voters in the middle. Okay. And the distortion of majority rule on this instance is 3. Okay, so this is a canonical example. I think Elliot referred this to some earlier work, but I just pointed to his paper. Okay. All right. Good. So what's the problem of this instance? Right? Why are we incurring such a high distortion? Okay. So it turns out one way to interpret this is to ask about. One way to interpret this is the green figure is not of the people. There's no voter sit at his location, right? Okay, so it turns out on this particular voter distribution, had we drawn the candidates from this distribution, the winner would always be the socially optimal choice. Okay, so by going from worst case to average case, you are able to eliminate this this particular instance at least. Now the question is, does this phenomenon hold more generally for all possible instances, or not? Okay, and the answer is yes. In particular, we're just going to use P to denote the voter distribution, and we're going to compare two cases. One is that P to denote the distribution of the candidates. Okay, one case is P is arbitrary; it could be different from the voter distribution, and the other case is P is equal to the voter distribution. Okay? So now this table, I'm going to list our results in this table. So, but first, let me go over the known results for this case. So the pretty much known results for this case is when the candidates are not representative. So why is this number 2 here rather than 3? It's probably worth to explain this so that we're comparing things on the same level. Okay. Now the problem is that when you construct a distribution over candidates, you no longer get to choose where you position them. The only thing you can choose is distribution, and then the candidates are drawn ID from this distribution. The reason for this change is we really want to compare the distortion, the worst case and average case distortion in the same measure in some sense. Okay. But anyway, the worst case example will look like this, except now that only with probability half, you get 2 candidates at different locations. And when that happens, your distortion is 3, otherwise your distortion is 1. So your expected distortion becomes 2. In this case, you can show that this is tight, okay, through some use of triangle inequality. But anyway, all right. So this is why the second column is 2. Now let me go over our results for this 2-candidate case. We showed a type bound of 1.17 roughly for the when the underlying metric space is a line, and we gave interval, which is 1.5 to 2 minus delta, where that is the worst case expected distortion when the underlying metric space can be arbitrary. Okay. All right. So again, this table is, as promised, shows you that your voting does become more effective when you have representative candidates, and the gap, the improvement depends on the complexity of the metric space. Good. So now let me briefly talk about these results. I think I have 3 slides on how you roughly prove this. So for the line metric space, you basically start with proving a lot of useful structural results about voting on a line. In particular, this is one of those structural results. It just says, when you have 2 candidates on a line, the candidate closer to the median voter is going to win the election. Intuitively, it just says, everyone, you can do a case analysis where they're on the same side or on different side, but in both cases, you can prove this structural result. You can prove many other structural results similar to this one. For example, one that's similar, but measures the social cost instead of who wins the election. And finally, you don't have to pay too much attention to the detail of these, but the point is, the important thing is you prove these structural results and then you use them to define a set of operations that gradually merges the support of your of a given instance while preserving the distortion, while weakly increasing the distortion. Okay? So by doing this, you pretty much show that the worst possible case for this average case voting distortion is a distribution of support 3. And once you get to distribution of support 3, you just you can brute force it by doing some case analysis and running some quadratic optimization. Okay, so just minimizing a quadratic function, and this gives you this particular instance that I'm showing on this slide. You can see that roughly what the instance is trying to do is pretty much similar to the worst case example, except now you have to put some voter at P3 in order to create this bad situation for this instance. Okay. All right, cool. So that summarizes of what happens on a line. Okay. Any instance can be reduced to support 3, and then you can bound things tightly for support 3 distribution. Okay, good. Now let me move on to the case where the underlying metric space is arbitrary. So here, mostly I just want to show this example of how the worst case instance look like. So you have one cluster of voters with probability mass half minus epsilon, and then you have everybody else shattered on the right-hand side. The distance between these little points are slightly closer to the distance from them to this big dot. Okay. Now, when you have two candidates drawn from the voter distribution, when you have on both sides, okay, so you have this blue and red, green figure. The green figure is going to win because everybody on the right-hand side is going to vote for him. Okay. On the other hand, the blue figure, her cost is actually smaller. Okay? So the distortion is 2 in this case. And again, it happens with probability half that you draw voters, one from left and, you draw candidates, one from the left and one from the right. So the expected distortion in this case is 1.5. Okay? I'm not going to go over the upper bound proof because I don't think it's tight, but roughly speaking, it just says, if your distortion is really close to 2, then your instance must pretty much look like this one, except depending on how far you are from 2, you have some room of placing an arbitrary set of voter distribution somewhere, a small fraction of voters arbitrarily in your metric space, and that is the reason why we can't bound this very tightly, but we can show that the answer is not 2. It's strictly smaller than 2. Yeah, I think this example is tight. I think the answer is 1.5, but we couldn't prove it. Could prove it is 1.5 in many special cases, but this is at the end of the day is the best we can do. Okay. All right. So that summarizes what I want to say about 2 candidates. Any questions?
Yeah, so I have a question. So okay, so I just want to understand a little bit of how far these can be pushed. So if, maybe on a line, if all the points in the space are candidates, so just, candidates, every single point is a candidate.
Okay. But you don't have this thing where the candidates are selected randomly from the population. Is that helpful? Sorry, I don't get what you mean.
Sure. Yes. So I guess I'm trying to think of the following, because my more general question is the following.
Right.
Are there other notions of representative candidates that would still give good results and might be used here? So one notion of representative candidates is the one you're using, but another one would be more like proportional representation in social choice, or maybe something like if there's a bunch of voters which are grouped together, then there's going to be at least one candidate very close to them. So for every
yeah, go ahead.
Yeah, so I mean that's basically I mean I guess that's my general question. So is there some other notion of representative candidates, like maybe there's a lot of candidates, or maybe for every group of voters, there's going to be some which please them reasonably well. I guess you could go back into this decisiveness stuff, then. That becomes.
Yeah, exactly. So, this is the special case of decisiveness where alpha is equal to 0, alpha decisiveness where alpha is equal to 0.
Okay, but it doesn't have to be exactly that. It could be something like for every set of voters that is large enough, again, just like proportional representation and social choice, for every set of voters that's large enough, there exists at least one candidate, so that they're the better choice for them than any other candidate.
Right. That is an excellent question. This is an open problem at the end of this talk, of course. I can tell you what we tried. So we tried to work with one notion of so you can have this knob called alpha, and then you can have alpha decisiveness, right? The other thing we tried was you can have some distance measure on how far away, how dissimilar the voter population is from the candidate population, and then you can ask how does the distortion degrade as they get more dissimilar. So there's some partial results there, but it's not very clean. So eventually we decided not to include it. But also it's also hard to study sometimes. There you probably go with Earth mover distance, I guess. But yeah, I'd say the most natural is Earth mover, and then it's definitely an interesting direction, but we weren't able to get a very clean and tight results back then. So yeah, and that's what we've tried. And also, all the other notions out there, it's worth exploring all the other notions out there. And I think, they're all great. The other thing, also one more thing like that is sometimes we've also looked at another model where you vote, there's a perceived location and there's actual location. You might have a parameter controlling how, what's the error in that. And then you can, when people vote, they vote with the perceived location. But when you compute the distortion, you do it on the actual location. So you can ask that too. But anyway, all of these are putting some restrictions on the, or introducing more variables to this metric preference voting model. And you can ask a lot of questions.
Okay. Thanks.
Yeah, cool. All right. Okay. Any other questions? Okay.
I have a quick question. So, so instead of looking at the average case over the candidates coming from this distribution, if you look at the worst possible choice of k candidates out of, or m candidates out of the n voters, initially I thought that your arbitrary p basically answers this. Is that correct? The non-representative p distribution that you look at, does that have any randomness left? If you look at the worst p, you can just fix k locations, and you can just say that these are the only k locations that have any positive probability. And then if you have to choose k candidates without replacement, then these will be the only ones.
Yeah, so that's a great question. I saw you type it in the chat window, but I forgot to answer.
Right.
So the issue with that is, if you think about the worst case 3 example, so what happens if I just put a tiny, like a negligible probability mass on the right-hand side, that will allow you to select a candidate there, right? Because you're selecting k out of n candidates without replacement, but it wouldn't be any different. Your distortion would still be 3, right? So that's why, that's why it won't be as natural.
But is it clear that, I see, okay, yeah. No, sorry.
It doesn't do anything. But you can certainly ask about a question like this. You can, you don't have to do the expectation for sure. You can do some other, instead of doing average, you can do other things. You can do other means on this. You can do geometry.
Right. I suppose when the number of candidates is comparable to the number of voters, then you might be able to show something nice. Right, because then you would actually need to have a substantial probability, voter mass at a location to select from that location.
Yeah. For example, to eliminate the problem I mentioned, you can say that you can only select a voter there if there's more than 1/k or more than 1 over 100K or something, probably massive.
Right.
Perfect.
Yes.
Right. Cool. Okay, so I'm gonna move on to the next part, which is voting with multiple candidates. Okay. So good. So we're still in the same setting where we consider candidates drawn IID from the voter population. Okay. So we're going to focus on, so these are the notations. We're going to focus on elections with N candidates and M voters, although we pretty much never use M. So just remember there are N candidates. Okay. We're going to focus on a family that includes a lot of the commonly used voting rules that are called positional voting rules. I'm going to define soon. Okay. In particular, we're interested in what are the voting rules that have constant distortion when the candidates are representative. More specifically, that means the distortion of your rule does not scale with N or M. Okay. All right. So what is this family of positional scoring rules? What that means is instead of voting for your favorite candidate, you have the ability to choose a numerical score, preferably, actually, I think it's required that it has to be monotone. Choose a score for each candidate on your, each candidate, depending on their position on your preference list. Okay? Not on their identity, but only on their position. And every voter shares the same scoring vector. Right, it's easier to go over some examples. So plurality just have this vector that gives 1 point for the top candidate, for your favorite candidate, and 0 for everybody else. Veto, where you just hate the worst candidate for you just vote 1 for everyone else and 0 for him. Now border is, the border scoring rule is a common rule that, is more smooth between plurality and veto, where you give the highest number of points for your favorite candidate, and then your score goes down gradually for down the list. In this talk, we're going to normalize everything to be between 1 and 0. So this is the scoring vector for Borda. You can have K approval, where you approve the first K candidate. Okay? There's some voting system called Dundell, which is actually used in Nauru to decide their Congress, I think. So this is some rule that's actually deployed where you vote 1 over I for the candidate who's ranked I on your list. Okay. All right. So our result here is we give a clean and tight characterization of which voting rules have constant distortion. To be able to talk about that, I need to define something called limit scoring rule. So that intuitively just says when the number of candidate goes to infinity, because we're studying the asymptotic behavior of distortion of different voting rules, how does this scoring vector look like when n goes to infinity? In particular, for plurality, it looks like this. So you have the function is equal to 1 at 0, and then it's 0 everywhere else. Okay. All right. Yeah. So you can draw the same figure for some of the voting rules I mentioned. Veto look like this, and border look like this. Okay, now what's the characterization result? It just says, whenever g is not a constant function on 0, 1, then your voting rule is good. Your distortion is not going to scale with the number of candidates or number of voters. It's going to remain constant. Okay? The constant, of course, depends on the shape. The upper bound for the constant depends on the shape of your function. Okay? Now, when g is constant on this on the open interval 0 and 1, but it's not equal to 1, okay? In particular, for the case of plurality, you're going to have a non-constant distortion. It's going to scale with the number of candidates. Okay? Now, when this is equal to 1, we have a more subtle condition that I will not talk about here. Okay? But there's a dichotomy there too. Just I won't mention. Okay. Now, armed with this characterization result, you can just basically connect voting rules to these functions, and then you can immediately, it follows immediately whether they have constant distortion or not. In particular, plurality, Dondel, and K approval have constant distortion. They do not have constant distortion. K approval for constant K. None of these have constant distortion. But if you have K approval where K is a constant times n, then it does have constant distortion. And same holds true for Borda and Vito. Okay. So Vito falls into this category where a more detailed condition is needed. But yeah, pretty much armed with this characterization structural result, you can just quickly decide whether these rules whether they're good or not in this average case model we study. Right. So these are the results you would get by applying this characterization result. In particular, you can compare them to the previous result by Elliott et al. On this when they studied this in the worst case. Okay. In particular, plurality and Borda had a linear dependency on the number of voters in the worst case, but they behave differently in the average case. And this infinity just means Vito in the worst case, the distortion of Vito in the worst case scales with m, scale with the number of voters. It's not even bounded by n, but when you go to average case, it is bounded by the number of candidates you have. Okay. All right. That concludes what I want to say about multiple candidates. Any questions before I move on to conclusion? Well, there's no conclusion. Move on to open questions. All right, good, cool. So, so first I'll start with the general conceptual open questions. So one is, people asked about this already. So it's just what are the other notions that make sense? And I mentioned this, you can ask for the degradation question. Okay. And also you could ask the average case distortion in other problems, for example, bipartite matching, and see whether this allows you to distinguish your different algorithms for those problems or not. Okay. It might offer some new perspective. And for more immediate technical open questions for two candidates, I think it's just closing this gap. So it's actually, I would be very interested in seeing this result. In the same way, I think closing the gap, having a tight bound of 3, but in the worst case is an amazing result. I think similar here, but I don't think the technique would apply. But I think the answer is 1.5, but I don't know. Another question for two candidates is you can put try to put another row in this table between the line and general metric space. You can have a metric space that's somewhat restricted, and you can ask how does this number go from 1.17 to 1.5. An example would be d-dimensional Euclidean space. Okay. For multiple candidates, I think the question I like most is just what can you say about non-positional voting rules? And with that, I'll conclude and take questions.